our own language when talking about things, and then one needs to reset this later. This is why the first lecture, it's very introductory and it's gonna be mainly slides. I'll try to make it to the hands-on part, while the other days I like to do the other way around to try to minimize a little bit the lectures, concentrate into the essential aspects. I'm going to introduce effectively one kind of network architecture per day, and then we're going to try it on a very same specific problem. So we introduce a problem today, and then we're going to play with this data set across the full set of lectures. So let's start with the general introduction what machine learning is. So this definition is taken from Wikipedia, and it's basically a very nice way of saying that rather than programming a computer to do something, machine learning is a way for an algorithm to be adapting to a specific data set and learn from the data to find the solution, rather than coming to the solution through a pre-compiled set of rules. So the way this works is that you have in the case of supervised algorithm, at least it's the easiest way to explain it. You have some training data set and you have a question. And for this question on the training data set, you also have the answer. And then what you like to algorithm is to learn the function that goes from your input, so your data, to your true answer as closer as possible. And this is done by taking the algorithms, structuring the algorithm as a set of degrees of freedoms and then are adapted in order to make the prediction out of the algorithm to match the true answer as close as possible. So somehow you get a probabilistic answer, not a rigorous one, but this probabilistic answer can approximate the true answer depending on how good you are for very, very complex problems for which a normal answer doesn't exist. Typical example, computing vision. Now, there are many flavors of machine learning. And of course, these days, when you think of machine learning, you immediately think it's super deep, complex neural networks. But the essence is in some sense architecture independent. Certainly until the 80s, shallow neural networks, so neural networks with one layer, thing that you see in the middle of the slide, were the dominant ingredients, the dominant tool for machine learning. But in the 90s, alternatives to these emerged, support vector machine and decision trees with boosting that outperformed the shallow neural networks. So across the 90s, at some point, people just stopped talking about neural networks, and this started again very recently. Now it's 10-ish years with the resurgence of deep learning. Now, typically, you have a two-step process. So you have a learning phase where you take your algorithm and you try to optimize it, and then you have an inference phase when you use the algorithm. The inference has a lot of problems, the issues, interesting challenges to discuss, particularly if you think about the LHC, is how you take these algorithms and you run it in real life, which if you are sitting on your laptop, okay, it's feasible, but if you are in a trigger system of a detector, it's a little bit of a more complicated business. On the other hand, it's not going to be the topic of these lectures. So we are assuming that you have infinite computing power and infinite time in real life to use the algorithms, and we're asking ourselves how you get to the algorithm. So when you train an algorithm, you have different kinds of algorithms you can try to train. These are three examples there. Supervised learning is when you do have a data set for training for which you also have some answers that you want to target. Unsupervised instead starts again from some data set, but in this case, you don't have the answer. So what you're trying to do is you're trying to learn from data. So in the first class of problem, typical examples, classification, signal versus background, regression, you want to measure the energy of a particle. While in the case of the unsupervised, typical problem is a clustering problem. I give you data of some kind and you want to cluster objects which are alike under some metric that you want to optimize for. Typical problem of clustering that you can imagine in particle physics is the reconstruction of particles. Now, there are other kinds of learning. One which is very, very famous these days is reinforcement learning, because this is basically when machine learning touches AI research. It touches so much that nowadays, unfortunately, AI is now used as a synonym of deep learning or machine learning, which is a very bad thing to do, but it's very, very hype. So reinforcement learning is basically the process by which you have a real life situation and you want to train an algorithm to take decisions. Typical examples, playing video games. And then you have a simulator, or you have somehow a way to repeat the same situation several times, and the algorithm has to go through this and try to solve the issues. Reinforcement learning had some applications to energy physics, but I have to say that most of the things that we do are supervised problem solving, and unsupervised is now getting into the radar of, let's say, the general community. So in energy physics, as I said, the classification regression, so supervised learning are the two most popular topics: particle identification, signal or background classification, measurements of energy, and so on. And one thing that I would like to stress is that these things have been extremely functional, for instance, to discover the Higgs boson. So, of course, at that time, we were not doing deep learning. Deep learning, as we will discuss later, is something that people typically trace the t equals 0 of deep learning to like 3 months before the Higgs was discovered. There is a paper that's considered the first paper on deep learning that basically opened the way to all the developments that happened in the last 8 years. But of course, at that time, we were busy doing something else, which was discovering the Higgs, and we didn't really notice that. We woke up 2 or 3 years after. But at that time, we were already doing machine learning, because we were using, for instance, boosted decision trees to classify photons and to discover X to gamma gamma. So something that people tend to not to appreciate, and this is because I mean, the Higgs signal the Higgs search was so well prepared that the discovery would have happened regardless. But the fact that we could use these techniques to discover the Higgs boson anticipated the discovery. If you look at the physics TDRs of ATLAS and CMS, and you do the math to scale what was the expected luminosity and expected energy of the collider and so on to what happened in reality. So you go down from 14 TeV to 7 and 8 TeV, and you update the number of femtobars that would be collected. There's no way the search is the people, the two Goldilocks channels, gamma gamma and for leptons, would have discovered the Higgs boson by 2012. The reason why this happened is summarized in these plots, that by using machine learning, we basically anticipated by a factor 2 the statistics, the discovery in terms of amount of data that you need. And so, of course, we would have discovered the Higgs boson, but it would have been 2016. And you say, okay, what's the big deal? The big deal is, first of all, it's money, but it's also PhD for people who are attached to the project and need data to graduate. So I think that it was a very successful story, and in some sense prepared the community to accept the fact that machine learning can play a role when we're dealing with high energy physics, and then eventually to transitioning to deep learning, which is what is happening now. Now, typical problems that we discussed, that I mentioned before in high energy physics, classification. I give you a set of points, a set of items in a data set, and you want to classify them according to some given number of exclusive classes, and for which I tell you which are the classes, and I give you also the target answer for the training data set. Or a regression is the same thing, except that in this case, the outcome is not an exclusive, a discrete answer, which class an item belongs to, but a continuous answer, for instance, the energy of a particle. Clustering is when you're trying to put things together by similarities that you want to learn from data. It's typical data mining approach. You could imagine imagine that you didn't know anything about the physics underlying the LHC collisions. You could still try to put together collision events that look like each other. The problem is to define the metric, and this is what clustering does. And sometimes clustering is approached with a kind of networks that if we manage, we're going to see on the last day, which are called autoencoders. And autoencoders are basically decompression algorithms, which are also used in other contexts, for instance, in dimensionality reduction. It's basically like a principal component analysis, except that it's nonlinear. It can learn nonlinear data compressions, and you can represent some n-dimensional input in a smaller k-dimensional space, retaining the most relevant information. And it's interesting concept also for like computing problems like reducing the displays of the LHC data and so on. Now, today we'll be discussing mainly about supervised learning. And for the rest of the lectures, we'll get into unsupervised learning, data compression, and so on in the last day. But the idea is to focus on supervised learning, focus on a specific problem, and show you different architecture in order for you to learn the basic of deep learning architectures. So if you think about a typical problem in IRG physics, I give you a data set, which I summarize through a set of features, which are the x1, x2 in this example. In real life, could be the energy of particles, the missing energy of the event, could be the multiplicity of jets, the multiplicity of leptons. So when we talk about features, we talk about the physics variables. And then I ask you, using these quantities, separate standard model background from a possible BSM signal that I tell you, let's say, I don't know, a gluino. You go there, you simulate your Monte Carlo, your signal, and your backgrounds, and then you end up with dots, which are the blue and the orange dots in some space. Then you want to separate them. You can just apply some rectangular cut on x1 and x2. You can do something smarter and draw that line that you see in the middle, which is still a linear discriminator. Or you can even be more aggressive and try some nonlinear discriminator. Now, how you decide what to do and where you draw this line. This is basically what the problem you're trying to solve when you run a classifier. So in the case of the linear discriminant, for instance, what you want to do is that you want to identify the boundary plane that maximizes the separation between the two populations. And you can do it in a very simple example, which is the logistic regression, which is an interesting example because it gives you a little bit the philosophy of the problem we're trying to solve. So you have your n-dimensional input, and you want an output, which is basically 0, 1. And the way you want to model the probability of x to corresponds to 0 or 1 is through the logistic function that you see there. The idea is that when the exponent term in the denominator is large and positive, that p goes to 1, and when it's large and negative, it goes to 0. And so that sigmoid function can incorporate this kind of behavior. And the name of the game is to find the optimal direction of that plane. Now, if you think about it as a Bernoulli problem, basically you're trying to find the probability of a process that can give us an outcome 1 or 0. And so you would start with the likelihood, which is the equation in the top of the slide. And now you want to in statistics, what you do is that you write down your likelihood, and then you look for the parameter p that maximizes your likelihood. Given the observations that you have, which is how many objects are probably one, how many objects belong to class 1, and how many objects belong to class 0. So maximizing the likelihood equals, or it's equivalent to minimizing the log likelihood. So you write this down, and doing so, you end up to that equation in the bottom right, which is the binary cross entropy. And if you look at all the deep learning literature, this is basically the most frequent loss function used when you train a classifier. But very little detail is given on the fact that this is a one-to-one. What you're doing is that you're running a maximum likelihood fit on basically on a binomial likelihood. So it's not like that these loss functions come from nowhere. They come from a very, very understood and classic physics statistics problem. Now, the problem is how do you minimize it? And this is where the computer science comes in, because so far, this was basically a very minimal problem that you find in any statistics book. Now, when you want to minimize that function, you end up typically to work with a lot of parameters, because your W parameters that define the plane where you want to cut depends on the dimensionality of your problem. And the problem is to find a recipe to minimize your loss function that works and scales when the number of inputs go very, very high. And this is done typically with a gradient descent algorithm. So you sit in some point, you compute the gradient, and then what you do is that you descend the valley just going opposite to the direction where the gradient is maximum. And you do this taking a step which has size eta, which is the learning rate. And you understand that the problem is very practical. I mean, it's how big you take eta determines how big is your step and what's your granularity in understanding if a point is better than another or not. If you take eta to be too large, you make big steps. You might do very good processes at the beginning, but then when it's a matter of finding fine-tuning the position of the minimum, you might end up. There is a question. I'll take questions in a bit when I'll pause a little bit, if this is okay. So, and then what I'm saying is that if the step is too big when you're doing the fine-tuning of the position of the minimum, you might miss it and just end up to some other valley of your loss function. And so the typical algorithms that work effectively for gradient descent is when you're trying when you run your gradient descent is to adapt the parameters of the algorithm, for instance, the learning rate, along the running of the algorithm. And of course, gradient descent itself is very, very effective, but it's also very, very slow, because when you compute the gradient, you have to do it with respect to your full data set. And every modification that you make of the parameters requires you to rerun on the full data set. So the next evolution of this is to parallelize it through stochastic gradient descent, which is the algorithm that nowadays everyone uses in some flavor. And so how this works is that you take your data, you split them in batches, and then you compute the gradients in the different batches. Of course, the idea is that when you do so, you restrict your calculation on a small batch, and then you can parallelize across the batches, you gain time, but you introduce some noise, because when you evaluate the gradient on some small data set, you are more subject to fluctuations in your data set and so on. And so the trick there is that you would then afterwards average across the gradients, and you will move across the average direction of the gradients. And you can show that this eventually will converge to the right decision. Typically in a typical problem, it will converge faster than with a normal gradient descent algorithm. Of course, sometimes it does not converge, and then this is when it becomes a little bit of a black magic. But what you have in literature, that there is a very, very active field of research in how you basically, starting from stochastic gradient descent, you modify the algorithm, specifying recipes in which the parameters of stochastic gradient descent evolve and adapt. For instance, typical thing is that if you have a SGD plus a recipe for evolving the learning rate, you have your own minimization algorithm, which could be Adam, Ada grad, Ada delta, whatever, Hermes prop, whatever people are using these days. A typical choice in this case is Adam. I think it's the one we have in all the examples they provide for the hands-on. So another typical problem that you will have is I give you points, y and x, so a scatter plot, and I ask you to model the relation between y and x. And of course, you could just say, okay, this is a straight line. If it's a linear problem, then this means just finding the coefficients of the A and B of that line. But the problem could be more complicated. So you might be looking for some nonlinear relation. And what people do in that case, that they still formalize it as a linear problem, but the problem is formalized as a function with the function phi of your x, which could be nonlinear. So with a kernel function. And a typical idea is that given your model, so your line, the points will disperse along the line with some sort of Gaussian dispersion, which is, for instance, the hypothesis behind the chi-square fit. And so you try to model this. You say that the relation between x and y is through some function h, which is that linear function on the top, plus some noise, which you describe as a Gaussian noise. And then if you write down the likelihood of this, means that for each of the points that you have, you would write down that probabilistic Gaussian dispersion. So you have a product of Gaussians. And then if you write the dispersion, which is this E parameter, as a difference between the true value y and your model h, you end up with this kind of function. And then, as we did before, you would say that the argmin of the -2 log likelihood, if you think about it, because of the properties of the Gaussians and so on, and end up being the argmin of the difference there, under the assumption that we make for convenience that the sigma, so the dispersion, is not dependent on where you are on the x-axis. So the dispersion around the model, if the dispersion around the model is constant, then minimizing this kind of likelihood is the equivalent of minimizing the sum over your data set of the true value minus the predicted value square, which is called MSE, mean square error, and it's the regression that everyone uses, the loss function everyone uses for regression. This is another example of why people do things mainly by example. They look at what other people are doing, and then they tend to forget the underlying assumption. When you use MSE as a loss function, you are implicitly assuming that your model, the dispersion of your points around your model, are independent on the quantity that you're looking at. For instance, in physics, this is never the case, because if I give you, I don't know, you want to regress the energy of a particle, you want to learn, if you want, the response of your calorimeter, and the response of the calorimeter is a function of the energy of the particle. The percentage response of the calorimeter is a function of the energy of the particle. Your detector for electrons behaves better for high energetic electron than for low energetic electron. Your detector for the muons is the other way around. It behaves better for the low PT muons and for high PT muon. But if the PT is too low, it doesn't behave that well as well. So this assumption is not even valid there. So if you want to regress the energy of a particle with MSE, you're making a mistake because you're introducing a function and you're introducing an assumption which is wrong. But if you look at the literature, nobody cares and everyone uses MSE, which is not correct. So this is to give you an idea that when you read a paper about computer science and machine learning applications, you have to be very, very careful that when you apply this to high energy physics and in general to science, many of the underlying assumptions which are valid and justifiable in the context break down in your hands, and you need to somehow adapt not just the methodology, but also the ingredients that go into the methodology to fit your case. In this case, for instance, what you would like to use is a sort of a chi-square. So you would like to retain the dependence of sigma on x, and then you redo the math and you end up to a different kind of likelihood. I think that, yeah, this, when you will get the PDF, this is a link. There is a paper that we wrote where we did exactly that. And then, of course, it's not rocket science. I mean, everyone is doing that when you know that you have to do it. So in a nutshell, this is the kind of problem that we're trying to solve. I give you data set, I give you the true answer. You build out a model that from the training gets to the prediction. Using the prediction and the true answer, you compute a loss function. So some function that quantifies how many times you get it wrong. So if you want a metric for how far your prediction is from the true answer, and then what you want to do is that you want to minimize that loss. That's what a training is. And in practice, when you do this, typically what people do is that they take a data set and then they split it in 3 chunks. Some like 60% of the data are preserved for training. And then the remaining 40% are split in 2 halves, so 20-20. One is for validation and one is for test. So training and validation enters the training itself. So the learning process is based on the training and the validation data sets. While the test, you put it on a side and it's your ultimate proof of the fact that the algorithm is meaningful will be done with the test. And in practice, what do? You take your data set, you take some initial configuration of your points, and then you run your stochastic gradient descent looking at all the data set that you have. That's called an epoch. And then you do it again, and then you do it again and again and again. And every time you start an epoch, you inherit the model configuration from the end of the previous epoch. And then as a function of the epoch, you should see that the loss function goes down. And there are 2 loss functions in the game. The one for the training data set itself, which is the data set that you use to compute the gradient and decide where to go. And then there is the loss on the validation data set, which you take it as a side, as a cross-check. And the idea is that if you are doing things right, these 2 curves should go down together up to some point that the learning basically flats down. And typically what people do is that they implement what is called an early stopping algorithm. So they look at the last, I don't know, 10 epochs, and if the validation loss didn't improve, given some tolerance, across, let's say, 10 epochs, which is called the patience, then you just stop the learning because you're not learning further. Okay, we will see an example of this. Now, what can go wrong? There are many things can go wrong, but they typically tend to go wrong in 2 directions. In one case, you basically were too strict in your parameter setting, and then you end up having a model which is not complex enough to catch your problem, the solution to your problem. Typical example, if you have a relation like the one in the figure in the top, which is extremely nonlinear, and you try to fit that with a straight function, you will miserably fail. And in this case, what's going to happen is that you might find some minimum value for your parameters, but the value at minimum is big. So which means that the loss is still big. So your loss function is going down, you're learning something, but eventually it saturates very early to a big value. And in this case, people say your model is biased. Instead, if you do the other way around, which is you put too much complexity to your problem, then what could happen is that you might end up being able to fit every single point, like the blue model on the right image on the top, that if you see passes through basically each single point that you have there. But you do understand that this is not a good solution because it's basically trying to follow each statistical fluctuation in your data. So while the loss function for the model on the right is better than the one on the model on the left, the model on the left clearly is more robust because it better generalizes. If you take another data set which will have different statistical fluctuations, the model on the left would still work, the model on the right would break completely. And this is typically seen in your training so what you will see is that you will see the loss function for the training data set that goes down and keep going down and down and down, which means that you're basically learning not only the solution to your problem, but also all the fluctuations of your specific data set around that solution. But then the validation data set will not follow because the validation data set comes with its own statistical fluctuations, and the statistical fluctuation pattern is different, and then you will just not decrease. And in this case, what one says is that you're overfitting. So you don't want to underfit, you don't want to overfit, you want to stay in the middle. So you would like to see that the orange and the blue curves go down together. And this is a little bit how you find the bias in the two things. In general, you can imagine that your error, your final error, so if you want the variance of your model with respect to the true prediction, has three components. The one component is the intrinsic noise that is in the given data set that I give you to test your model. And then you have a model, another contribution to the error, which is due to the bias, and another contribution to the error, which is to the variance. And while on the first thing, which is the intrinsic statistical noise of the pro data, you cannot do much, your task is to try to minimize the red and the green. And the problem is that the two things don't minimize together, so you need to find the optimum in the middle. And this is where designing the model becomes tricky, because too big model tends to overfit, too small models tend to underfit and to be biased. And for this, people play with regularizers, which is the last ingredient if you want of your training. Typical way to regularize a learning process is to add a penalty. So you add a penalty to your loss for each parameter which is used. And a typical thing that is what is called an LP regularization, where P is a number. It can be 0, 1, 2, and it's basically the kind of penalty that you see is the one which is represented on the right. P equals 1 means that basically you're putting an absolute value of the weight as a penalty. The bigger is the weight, the more penalized you are. P equals 2 as a quadratic weight, and so on. You can do P0, which is basically a delta function, and so on. This is something people have been doing. But another, now I pause, but there are other ways to do regularization that we'll see in the next, which are a little bit more, less mathematical, but more intuitive. And we'll discuss this later. So I'll pause here for questions.
I can unmute in case someone wants to ask, or you can write it.
There is a raised hand.
Yeah.
Hi, yeah, thanks. I just have a quick question about the learning rate. So is there a mathematical way to optimize your learning rate so as not to over or underfit? I mean, I've seen it done, of course, just by trial and error, but yeah.
It's extremely, it's an empirical thing to where you put your learning rate. People sometimes what they do is that they treat it as a hyperparameter, in the sense that you would do your training. You can do your training functional to, so basically as a function of your learning rate, you would do a training, but then you repeat the training many times and trying to model the dependence of your learning on the learning rate, and you do basically an hyper, so you do a minimization of the loss as a function of the learning rate, and for each point you will minimize the loss. So this computationally becomes more expensive. It's not really done analytically because it's extremely problem dependent, but with things like Bayesian optimization or genetic algorithms, people have been playing with these things, and you try to basically find the setup, not only for the learning rate, but in general for all the choices that you have to make when you design a model. Because, I mean, even designing a stupid neural network with like fully connected layers as the one we will see, you have to decide how many layers you put, how many neurons per layer, which kind of activation function. We're going to see these things in a little bit. And then very quickly you realize that there is no right and wrong. And this is extremely empirical in this sense. People are trying to give a sense of a mathematical reasoning of why certain models work better than others, but I would say that to a large extent, this is extremely empirical so far, and there is not really good answer of why these networks learn so well.
Okay, got it. Thank you.
Anything else? No? Okay. So we go to deep learning. So what is deep learning? So let me first minimize the, okay. So deep learning it's a very fancy way of saying neural networks which are not just input, one hidden layer and output. So more complex architectures than the shallow neural networks. Everything which is not a shallow neural network is a deep learning algorithm to a certain extent. But the typical thing that you imagine is a neural network which has feed-forward structure. So input comes from the left and get out to the right. There is no loop. And you have neurons arranged in layers, and there are more than one hidden layer. So deep is more than one hidden layer, effectively. Now, these algorithms, there is nothing conceptual. Okay, now there is more conceptual progress, but at the very beginning, there was nothing conceptually different between this network and the shallow ones. Now, of course, the problem was computational. Nobody knew how to do the loss function minimization for this beast, until the day that people realized that graphic processor units could be used for this. So the implementation of what is called a backpropagation algorithm, that is an algorithm that allows you to find effectively the gradients. So it's a chain rule algorithm that allows you to write, for instance, the gradient as a function of the parameters in the first hidden layer, as a function of the gradient of the next layer, which is a function of the gradient of the next layer, through a chain rule. And at the end, what this means is that once you compute the gradient of the last set of parameters, then you can back propagate. You can basically, going backward, you can compute the gradient to all the other parameters. And this algorithm implemented on GPU is super fast. And so it's not that the algorithm was new. It's not that the GPUs were new. What was new was understanding that that algorithm on the GPUs was the key to success. And at that point, the new technological capability opened up a new world, which is typical in many fields, that people have a lot of ideas, but if you don't have the technical breakthrough, the idea stays on the paper and they don't enter real life. Now, they entered real life, and basically this is everywhere now. Image processing, text, speech recognition, clustering algorithms like Netflix telling you what you want to watch next, reinforcement learning, the famous case of AlphaGo, the deep mind beating one of the Go masters, and so on. Now, in hierarchy physics, of course, you can say, I can just take whatever I was doing with boosted decision trees, and I can do it with deep learning, which is true. I mean, it's just someone gives you a faster car, you get out of your car, you get the new car, you go faster. On the other hand, deep learning is extremely good in something that the previous algorithms were not good at, which is to generalize to very, very large dimensionality of the inputs, which means that deep learning allows you to run directly on the raw data. Computer vision is an example. You don't have to take an image and then compute quantities out of your image and then give it to the algorithm. You just get straight the full image, and then the algorithm will figure it out. And so there are many things that you can do that before you could not do it. Like you can use this as a way to do like event generation, to replace Giant and to like do Monte Carlo generation with it. You can use it to search for new physics as an anomaly detection algorithm. You can basically shape your problem in such a way that you can train, you can minimize, you can only find the solution to your problem, but you can do so while at the same time you try to minimize systematic uncertainty associated to it. You can use reinforcement learning for jet grooming. I mean, there are many, the field of applications is much more diversified. So today we just discussed the feed-forward neural networks. It's more or less is what I said. There is no closed loop. Inputs get in on a side and get out on the other side. And your neurons are structured in layers, and fully connected means that a neuron of a given layer is connected to all the neurons of the previous and to the next one. And this is basically the classic idea of classic neural networks that people have been playing so far, except that you have more than one hidden neuron. So what you're doing is that you get a vector of inputs x, and then your first layer for each neuron I is basically a multiplicative factor of the vector. So you have a matrix of weights that the way you mathematically represent an hidden layer is a matrix of weights that multiply your vector, and then you sum across the index of the input. And then you add a bias. And this is the logic of an activation function. Sorry. Now, this is where the magic happens. Because here, this is a linear operation. And so you can only learn a linear transformation with linear operators. So your network will not be that good. The reason why you can go beyond linear function learning is because you put as an activation function a function which is nonlinear itself. And nonlinear doesn't mean that it has to be a sigmoid, which was the very first classic case. Nowadays, the most used activation function is the one that you see in the bottom left, which is called ReLU, rectified linear unit. This is a function which is y equals x for positive values and y equals 0 for negative values. It's two linear functions joined at one point where there is a discontinuity. So if you are clever enough such that the input to the activation function is shifted, is centered around 0, where the discontinuity is, then this very simple discontinuity allows you to learn very, very complex nonlinear functions. The name of the game is to use a nonlinear activation function and to shape your problem in such a way that the input to the function go and stress, if you want, the function exactly in the region where there is the nonlinearity. The other advantage of that ReLU function is that because of its simplicity, its gradients are easy to compute because basically it's a sine function times 1 or times 0. And so this goes super fast when you run it on a computer. Nowadays, basically nobody uses sigmoids anymore. And so your network becomes a function like that one, where you have a function of these combinations of weights and biases of your final x. And what you want to do is that you want to compute your loss function as a function of the w and b's, and you want to find the best sets of w's and b's that allows you for your y, j, to be as close as possible to the right value. Now, okay, this is what I just discussed. The activation function where the magic happens. Now, this is something. So basically, with all I told you so far, we could just now jump on the hands-on problem. But before doing so, I would like to show you a few other things. So first of all, dropout. Dropout is a very it's a poor man way of doing the regularization. So to prevent overfitting of your model. With dropout, you can basically forget about under training. Biases. You would basically try to put as big model as you can, and then you would use dropout to prevent the overfitting, which is the opposite problem. So how does it work? You specify a probability for dropout, p, 20, 30% is typical value. And then when you are training your model using stochastic gradient descent, your data set is divided in chunks. And the different chunks are evaluated. And when you do so, basically your library would remove connections based on probability p. And then you go from the fully connected model you see on the left to that model you see on the right, where some of the connections are just switched off. Because of this harassment that you're applying on your network, where you're basically taking out connections randomly, which means that sometimes you take out one connection, sometimes you take out the other one. So the model, the network that you effectively use is always different than the full model. So you're basically preventing the network. I mean, this is a hammer regularization. You're really preventing the network from overfitting because you are continuously dropping connections and you just don't make it possible to overfit. it's a very empirical way of doing things. It doesn't have a mathematical rigorous approach like the regularization that we saw before in the laws. On the other hand, it works very well. And when you use the dropout, what happens is that from you drop out in training, but then you restore all the connections in validation. It happens that the validation loss becomes better than the training loss, because of course it has more degrees of freedom. And so by definition, the overfitting, which is the opposite behavior, doesn't happen. So a typically healthy loss versus epoch distribution out of dropout regularized network should be the one on the right, where the training is worse than your validation. And another important thing is batch normalization. In the example that I have it, I don't use it, but you could, for instance, try and put it. So what does batch normalization do? For a given tensor as input, you would shift it and rescale it such that the mean is 0 and the RMS is 1. And so, for instance, batch normalization is good to do the trick that I was saying before, to basically recenter a given input to the region where the loss function is continuous. So I can imagine that if you have a loss, if you have a layer which is activated by ReLU function, you might want to use in the middle batch normalization. And so this is something that, for instance, is very used a lot with more complex architecture like convolutional neural networks that we'll see tomorrow. Other things is that you need to think about this mathematical operations as tensor manipulation. It's basically linear algebra. And so all the functions you can do with tensors are implemented, add, subtract, or whatever. But also you can concatenate arrays, you can flatten the arrays, reducing the dimension. These kind of things tend to be helpful here and there. And there are, in the typical library you would use, there are like, these things are pre-implemented for you. In terms of libraries to be used, there starts to be pretty much rich set of options. The examples that I put together use Keras, which is a library built in Google's TensorFlow. And it's a very nice way to start for starters, because every standard library is architecture is basically implemented. And with simple Python calls, you can build up your model. Then if you want to do, it's a very nice starting place, but then when you start to become very experienced, very soon you realize that you need more, then you need to go one layer deeper, and then you go back to TensorFlow, which is basically a generic tensor manipulation library that these days physicists are using, not just to do this, which is what the library was written for by Google, but for instance also to do, I don't know, maximum likelihood fits. And then the last thing that I was saying is that, as I told you, GPUs are a key ingredient in these things. GPU just let it go faster. I'm not gonna go through these slides, but in the examples that we're gonna use, we're gonna use GPUs as a default. You could try, for your amusement, to try to run the same thing on CPUs, and then you might see the difference. And then a few words, but before the words, maybe I wanted to introduce very quickly the problem that we're gonna handle, but maybe it's a good time to stop and get some question.
Yeah, there is a question. Let me activate it. Let's see if it works.
Hi, can you hear me?
Yes.
Yeah.
My question was about dropout. I did not understand it, actually. First of all, in this graph you have, what are the nodes? What are the connections? And so what does
the
it mean?
nodes are the circles. The nodes are the circles.
Yeah.
Each layer, and then the connections are those arrows. Okay.
Yeah.
And those connections are mathematically means that for each connection that you see there, there is some wij parameter are located and some bij parameter, bi parameter are located. When you switch
what
off
is the
the
correspondence
connection,
with
sorry?
your data set? What is the correspondence among the nodes, the connections in your data set?
The data set, so the input nodes are the input quantities. So for instance, if you give me a data set which has I don't know, moment of a particle px, py, and pz, then j will run from 0 to 2. J0, J1, j equals 0 will be the x, j equals 1 will be the y, j equals 2 will be the z. And then for each of these quantities, let's say that you allocate a layer which has 10 neurons. So you will have wij, where I runs up to 10 and j runs up to 3. So it's a 10 times 3 matrix. And bi is a vector of 10 components. And then you do this matrix vector product. You sum across the index of the inputs, and then you have a 10-dimensional vector out of this sum here. And then you sum to the other vector, component by component, and then you apply the activation function and you get 10 outputs. So this is what the mathematics of the thing. Now, if you add dropouts, what you're doing is that you are switching some of them, you're putting them to 0. And so they will not contribute to this sum. And so it's like if they were not there to start with. And
but
then
it is
yes.
you that decide how the output is made.
No, but dropout is a stochastic process. So what happens is that you allocate the full architecture. So you say, I want 10 nodes, fine. But then when you run with dropout, out of these 10 nodes, each node will have probability P, let's say 20% you decide, to be switched off during a given iteration of your stochastic gradient descent minimization. And then in the next iteration, it would be put back in to the value it had before being switched off. And doing so, you're basically disturbing your learning process, such that the learning process has more difficulty to learn. And so you are implicitly, you are preventing it to learn it too much, if you let me pass the expression.
And don't you have the risk that by eliminating some of the links, you may isolate some points, and so you throw them away from your learning process?
No, but the point is that this is done stochastically for the structure of the network, not for the inputs. This goes on the structure of the network. The inputs are always coming in. Okay? So, and the other thing is that it's done stochastically, which means that you keep changing the scheme of what it's dropped and what is not. And so the idea is that if you let your training go long enough, you will not have effects of this kind. Of course, this means that you are somehow, I mean, you're basically trying to drive your car with the brake on, and you might end up not finding the ultimate minimum. On the other hand, you have, practically speaking, less problems in terms of overfitting. And so you have to put less thoughts about how big your network is going to be. This is how people end up learning, I don't know, networks that have like 100,000 example and 100,000 parameters, and they don't overfit. Okay.
So the mathematics that is behind this kind of manipulation is no longer minimization and stuff, but rather graph theory.
No, you minimize, but on the fly, you mask out some of the parameters, zeroing them. It's the mathematics is very easy, because if you replace the w's by zeros, it's effectively you are changing the pattern of the graph, but it's not that you are changing the pattern of the graph. You just put some parameter to 0 and you do times 0.
Okay, thank you.
Once you have so if you had the network on the right, implementing it and using it would be complicated because, of course, it has a very scattered memory access. And so using the network on the right would be more complicated. But the network that you will end up using is the one on the left. Dropout is not something that you basically remove the dropout when you use the network. Dropout only comes in when you are doing the minimization. Okay.
Thank you.
Others? I saw at least another two.
Yeah, 1 second. Let's see. Let's see if it works. York.
So yeah, hello. So I have also a question about the dropout. So the idea about the dropout is to reduce the complexity of your model, so to prevent overfitting. So my question is, why don't we just use less nodes instead? So this will also reduce.
You could certainly. You
Sorry?
could certainly, but as I said, since it's similar to the question we had before. So the problem is that it's the same as for the learning rate. Is there is no right and wrong. So when do you stop? And you could do like iterative procedures. So you start with some network, then you try more, you try less, and then you monitor, which is effectively the kind of problems the kind of things we're gonna do. You monitor the loss versus epoch diagram, and you try to understand if the behavior that you see for the training and the validation loss are healthy. And based on that, you decide to change something, and so on and so forth. And so you could even say that you give the problem to a class of students like you have 60 people trying the same thing. Everyone would try, actually the exercise that I would like to try. Everyone tries a different one. And then we minimize, someone will get better results than the others. And that somehow, call it a genetic algorithm, effectively, a social algorithm. You end up finding this way a better model, just because you have many people trying different things until someone finds one that works better than the others. The advantage of using dropouts and things like that is that this is done automatically. So you don't have the problem anymore, because what you do is that you just put a ridiculously large number of parameters, and then dropout just prevents the network from overfitting. And then the only problem, and since you put a big number, you are not underfitting, and then you have one problem less. It's a very practical way to deal with the problem, which doesn't mean that you might not overfit. You might still overfit, so you will have to redo it a couple of times better, but typically you converge earlier to a workable solution.
So instead of the only advantage that's doing automatic, is there also the advantage that's done randomly, and that we add them again when we validate the data, so it has like a better performance at the validation data? Is this the
I mean, the fact that it's done randomly, it's basically the key of why it works so well.
Okay.
But it's not the only way of doing it. As I said, you could decide that rather than using dropout, you just put a regularization term in your loss that says, I penalize my network every time it uses a new degree of freedom. So you have the network which has all the parameters to 0 is the one that has no penalty. And every time you switch on a degree of freedom, every time you switch on a parameter, you might get a better solution. So your reconstruction loss, it gets smaller, but you pay a penalty because you add the absolute value of the weight to the loss. This is called the L1 regularization, and it's also a very reasonable way of doing things. It has other advantages, it has pros and cons. So these are just, I'm presenting you options.
Okay, thanks.
Anne-Catherine, do you still have a question?
Yes, I do. Thanks. I have a question about batch normalization. So wouldn't an appropriately complex deep neural network basically be able to do this for you? I guess my question is, why would doing batch normalization change the outcome?
In principle, yes. In principle, the network should realize that there is a set of parameters W's that would force the output to be in the region where there is no linearity, and it's convenient to be there and randomly somewhere else. But as you realize very quickly when you play with these things, that many things that work in the limit of infinite computational power don't work in practice. And networks need help to converge to the right solution. And this is why batch normalization, for instance, is something that you typically tend to do. Another thing which is very physics inspired is that whenever you know that there is a piece of information which is relevant to your problem, you should use it. Because it's true that there is a theorem that tells you that a network will learn it, but this is a statement that you have in principle. In real life, you will have to be confronted with the limited computational power because you're not Google. You need to pay the bill, the electric bill at the end of the month, and then you just want to make your learning process as effective as possible. And these are tricks to just make it easier. But the tricks can be very, very easy. Like for instance, imagine that you're playing with as input particles. Like you say, okay, you want to specify the topology of your event. You say dijet events. Say, okay, I have 2 for momenta. So I give px, py, pz, and e. For the 2 jets, all the information is there. True. But you could also say, instead, give pt, eta, phi, and mass, or pt, eta, phi, and energy, change bases. And you would say that the 2 problems are equivalent, right? Because the amount of information that you're putting is the same. You're specifying the 2 for moment of the 2 jets, and then you want to learn stuff about these 2 jets, you should be able to do it. You would soon realize that these 2 different configurations give different results. And, which is when things become counterintuitive, if you instead just give both of them to the network, both the Cartesian and the covariant coordinates, the boost invariant cylindrical coordinates, you will even get a better result. The reason being that it's true that the amount of information which is in px, py, pz, and e, and pt, eta, phi, and mass is the same. But the function that goes to transform one into the other is a nonlinear function that the network will have to figure out by itself. And learning, it might learn that function, but it might not. But if you know that that function is relevant, so if you know that pt is a relevant quantity in your problem, and you are giving as input px, py, pz, and e, it's true that pt is a function of those quantities, but you know that that function is relevant. You should extend your input, putting that function explicitly, and your learning will be faster, and you will get to a better result. So there are many things which are extremely counterintuitive, because effectively this minimization process is extremely chaotic, because it's a multi-dimensional problem, and when there is a piece of information that you know is relevant, you just put it there and then just asking and hoping that your network will learn it, because it might learn it, but most of the time it will not.
Okay, thanks.
Okay, so I think that, so so what I'll do is that I finish the slides, so we don't do the hands-on today. We'll start with the hands-on tomorrow. But I want to tell you a little bit about the problem that we're gonna handle, and a few of the things that the hands-on tutorial will do. So the problem we're taking is a typical problem for machine learning applications at the LHC, which is jet tagging. So I give you a sample of jets, and you need to figure out which kind of particle is that jet coming from. And there are basically 3 main classes of objects, but actually we play with 5 classes. You have classic UCD jets, which are the things that you see on the left, quarks and gluons, where you have a shower of particles, which is cone-like, fine. Then you have the bosons, the heavy bosons that decays to a couple of quarks. And if these bosons are boosted, these 2 jets get close to each other. And so you reconstruct a single jet, but it's actually the overlap of 2 jets. And then you have the top, which is the same thing, except that now you have the W boson and the B quark from the top. So you have 3 jets overlap. And now I'm giving you some information about these jets, and you have to figure out which kind of jets you have. And we're gonna play with 5 classes, which is quark, gluon, W, Z, and top. These are the 5 kinds of jets that you have in the datasets that we provide you. You could also do Higgs boson, B quarks, but that's not in the data we have. Now, a very typical way to address the problem is with physics. So you know the physics of the jets, you come out with quantities which can separate the behavior of these objects. So these are called what we call physics motivated high-level features. Typical example, jet mass, multiplicity of the particles, energy correlation functions. People have many options. And of these many options, we come out selecting 16 of them. And then with the 16 inputs, we come out with a model. This is an example of a model that you can decide, but you can have other choices like 3 layers, 64, 32, and 32-bit nodes, and each node activated by a ReLU activation function. And then in the output layer, I have 5 nodes for the 5 classes that I have. And then I use an activation function, which is softmax, which is basically a generalization of the sigmoid, in such a way that my 5 outputs are probabilities that sum up to 1, which means that given a jet, it has to be of one of these kinds. So a number between 0 and 1, such that the sum across the 5 categories is 1. So this is the model that we're going to play with. So the name of the game is to find the best configuration for this model, which means that given this model, you want to optimize its parameters, but you also decide that, for instance, you want to add another layer, you want to change the activation function, you want to use more or less nodes. This is really up to you. The only fixed thing is the 16 inputs and the 5 outputs with the softmax. Everything in the middle, you can change it. You can have dropout, you can remove dropout, you do whatever you want. Okay? Now, once you have such a model, the model gives you these 5 outputs, which are probability. So what happens? It was called the score of the network. It's that let's say that we're looking for top quarks. If I give you a top quark, the score should approach 1. While if I give you another kind of quark, the score should be low. So if you look at the distribution of the scores on your test data set, for the top, you should have a distribution, a peak somewhere at large values, and then there is a tail. And the background should have the other way around. So there is a place somewhere in the middle where you want to cut. And then you want to call all the jets which have a score larger than that threshold, and you want to call them top quarks. And then you notice that most of the jets that you will call top quarks are actually top quarks. They're called the true positives, this area here. And most of those that you will reject will not be top quarks, just the true negatives. But then there is this fraction of jets here, which are not top quarks, and you will call top quarks, it's called the false positives, and then you have the false negatives. Okay? So the idea is, where do I put this line such that I have the best jet target possible? And this is a very ill-posed question, because it depends on how much false positive you are willing to accept and how much false negatives you are willing to accept. In other words, with physics nomenclature, how much efficiency you are okay to lose and which kind of impurity or mistag you're going to accept. And so experimentalists typically are faced with the idea of, where do I put this line? Okay. Now, no, this is the thing I want to show. There are many metrics that people compute, like accuracy, which is basically the fraction of events which are correctly classified. So true positive plus true negative divided by the total. The sensitivity, which is the true positive divided by the total positive, which is we call the signal efficiency. Specificity, which is what we call mistag, and so on and so forth. But the most common thing that people do is this, is that they move the threshold, and while they move the threshold, they record the they record the dependency of the true positive rate, sensitivity, or the false positive rate, specificity. So your ideal tagger is a tagger that accepts 100% of your signal and rejects 100% of your background. So it's 1-1 in this diagram. And the line that you draw while you move this threshold is what is called a receiver operating characteristic curve, a ROC curve. And what you want to do is that you would like this curve to maximize, to approach basically being a square. Or if you want the area under the curve, AUC, you would like it to approach 1. So a typically metric of a classifier is a plot like this, where you have the mistake rate, so the false positives as a function of the true positives, and you would like to be more on the bottom right of this plot. And you would like to maximize what is called the area under the curve, but in this case, it's really the area above the curve. You will have to draw it the other way around to beat under. And you would like these numbers to be as close as possible to 100%. 100% is like the ideal tagger. Notice though that the AUC and ROC curves are a little bit of overestimated concepts, because there are things that happen like this. Look at this red line here. Okay, so the majority of the AUC is dominated by what's happening up here, but it may be in your problem or your physics problem, you actually have so much background, but also so much signal, that what you care about is purity. So you would like to have a very high purity, a very pure sample of, let's say, I don't know, W bosons, but because you have a lot of them, because you're running at 2035, 3 attobar no high luminosity, let's see. And so you don't care about saving statistics. You want the statistic that you save to be very, very background free. In that case, what you care about is this part of the, I don't know if you see my pointer, is the low efficiency, low mistag, so the bottom left corner of this plot. And so even if you have an algorithm that has an AUC which is better than the other, but it's downperformed in that region there, you don't want to use that even if the AUC is better. So when you read a paper and you say, oh, I have an AUC of 91.5 rather than 91.2, that's not enough to say that you have an improvement, because it might come from the fact that you just improved the region where the signal is about 1 and the background is about 1, which is physically uninteresting because it's of no use for you. So when you think about the performance, in the tutorials, we will use this tool, but this tool has to be taken with a grain of salt. And this is the summary of the lectures of today. And if there are questions, I take the questions. Otherwise, I show you very briefly the Jupyter notebook to start playing with. I think, okay. So now I want to share a browser. So, do you see it? I guess so.
Yep.
So this is Colab, colab.research.google.com. So if you log in there, you should get something like this. And then you can upload a notebook. And then you go under GitHub. There are slides that I will share with you that describes these procedures. But if you do Pierini tutorials, There are a bunch of Jupyter notebooks that pop up. Particularly, you care about the GGI January 2021 ones. The notebook one is an example that shows you a little bit some of the features of the data set that we're playing with, if you want to look at that, but it's just, you read the data set and you just make plots. Here you have a link. So this is notebook 2. There is a link to a paper that describes the data sets, the networks, and everything. Now, to run, how does it work? Do runtime, and you wanna change the runtime type to GPU. For today, it's not super relevant, but for the architectures of the other days, it's gonna be relevant. So don't forget about that. If you wanna play with it, try with and without and measure the difference, and you will be surprised. And you realize why NVIDIA shares on the stock market are going high. In any case, we set GPUs. Then this is a notebook. I mean, I guess you're familiar with notebooks. So you start running cells. I'm not gonna go into, okay, run a, here you say yes. I'm not gonna go into the details. These are like very standard things. But what's happening here is that this downloads the data set, and then each data set is scattered across a few files. So here I'm reading the files in and then just attaching the data sets into a single file. Unfortunately, we cannot run with the full data set because on the top right, you see that we have limited RAM and disk on Colab. We have to pay for one more. So if you want more, a way is that you could actually retrieve the full data set. So let me go back to the slides and tell you this. So in this, you see in the last slide, there are a few references. In particular, I really suggest that you read this book, which has everything you want to know. But the other two things is that this paper gives you, there are a few papers that describe the data sets and so on. This paper in particular is basically where I took the exercise from. And this is the address of the notebooks and things. And there is another address here that gives you a link to the entire data set, okay? Now, here we are gonna only play with a few files. So you see that we have two data sets. These data sets, which are called features, is the 16 features for each jet, and we have 50,000 of them.
Maurizio, maybe it's only me, but I don't see the screen.
Oh, sorry, I messed up with Zoom. Yeah, let me go back. Yeah, I didn't re-click. Yes, now you should see it. Do you?
Right, yes.
So we have 50,000 jets, we have 16 features, and these 5 things are 5 numbers, 0 or 1. So the reason why we have 5 of them is because it's called one-hot encoding. So for a given category, you have 1 if the jet belongs to that category, or 0 if it doesn't belong. I mean, computationally, it's easier to play with this because it's binary numbers, as opposed to saying, tell me 1 if it's category 1, tell me 2 if it's category 2, tell me 3 if it's category 3, and so on. So people use this one-hot encoding a lot, and this is what we're gonna do. So your target is effectively 5 bits, where of the 5 bits, 1 is set to 1 and the other 4 at 0, depending on which jet you're playing with. And you want to get 5 numbers in output, which get closer as possible to this target. Okay. Then in the next cell, I am applying standard libraries from scikit-learn, which is a data science package that allows you to split this data set in train and validation. Normally, I should split, as I told you, train, validation, and test. But since I didn't have so much to start with, I did just training and validation. And then I'm using the validation also for test, which is not super nice, but it's okay. And then here, this is the part that we care about. So here I have some import of some TensorFlow.keras functions. So for instance, dense is the fully connected layers that we discussed. Input is the input layer. Dropout is the dropout layer that we said. And then here I have a few special calls that I will describe later. Now, the shape of my input tensor is xtrain.shape. So it's 33,500 jets, 16 features per jet. And then I give this in input to a model. So these few lines are how I built the network. So there is an input array, which is the output of this operation, which is basically I'm allocating an input layer. And then there is a next layer, which is a dense layer with 40 nodes, an activation relo that acts on input array. And then I have a dropout layer that acts with some dropout rate, we just put it 0.25 to X. And I call this output X. So I redefine X. And then I keep doing this. So after I put a dense layer that acts on whatever X is now with 20 nodes. And then I activate them. And then I put dropout. And then a third layer with 10. Again with dropout. And then the final output, which is a dense layer, fully connected, with 5 outputs, activation relo. Okay? This, I don't know why it's there. We could even take it out. So this would be similar to the model that I showed you before. So 3 dense layers, 40, 20, and 10. And then I have an output layer, which, unlike the previous one, has an activation softmax, because we want numbers between 0 and 1. So once I define this flow of tensors, so we start from some input and then we go through all this chain, I define a model specifying model is something that is predefined in Keras here. I define the model as something that takes some input array and some output array. And if I run it, it doesn't complain, hopefully, which is fine. But then if I compile it, which is where the actual check of the fact that the previous code makes sense happens, when I compile it, I have to specify a loss function. And I specify categorical cross entropy, which is the cross entropy that we discussed before, but for multi-categories. And an optimizer, which is Adam, which is the most popular kind of optimization algorithm these days. But you could just write SGD here and you would run a plain stochastic gradient descent. Adam is basically stochastic gradient descent with some built-in rule on how to evolve the SGD parameters. And then I get my model summary. This is my model summary. And you see that you have all the layers. You see that the first layer has 40 nodes and 16 inputs. And so you have 680 parameters. If you do the math, it's basically the kind of operations that we're discussing before, multiplying the tensors and then adding the biases. So it should be 40 times 17. Right. So 40 times 16 is the weight parameters, and then another 40 for the biases. Dropout has the same dimensionality, but it has no parameter, because dropout doesn't have any learnable parameter. It's just some manipulation of the tensor. And then you keep going up for a total of 1,765 parameters, all of them learnables. Then I define a batch size of 128, which means that all my 33,000 whatever input data sets will be split in block of 128, and then the parallelization will be such that the computation of the gradients will be happen on blocks of 128 in the same time on the GPU. And then this is we do 50 epochs, so we do 50 passes on the data sets. And this is the training instruction. You take your model and you do model.fit, where you specify the X and the Y, and the validation X and Y. Then you say how many epochs, you say how big the batch size, the verbosity, okay, I put it 2 because otherwise it was too much. This is the thing which is a little bit more tricky to understand, which is the callbacks. So I want to give instructions to the stochastic gradient or to the minimization to what to do in particular circumstances. For instance, I want to reduce the learning rate when it saturates. When I don't know learning anymore, I reduce the learning rate by a factor 10. If basically there is no improvement over over 2 epochs. And you see that sometimes this happens because it gives you, okay, I'm reducing the learning rate to this number, okay? So on top of what Adam is doing, I'm putting an extra bit of it. And then I have early stopping, which means that if you don't see an improvement on the validation loss for 10 epochs, then stop. And then if you get not a number somewhere, you just stop because things are going crazy and you don't want to waste GPU and time. And after you have done this, at some point, this thing stops and it gives you this result. And then you see is that, okay, there was a first big drop of loss just because we started from some crazy point. But then you see that the training loss goes down as much as the epoch continues, and then it gets to 50 and it didn't early stop. So we could have done maybe more than 50 epochs. So this is not a completely trained model because you see that this still have some slope. The other thing that you see is that the validation loss is better than the training loss, and this is because we have the dropout. You could, for instance, do the exercise of removing the dropout and see what happens. And then these last 2 cells are just the code to make the final plot. And these are the AUC. Let me write. Okay. So you see that this is true positive rate as a function of false positive rate. So to give you an idea, an algorithm, a known machine learning based algorithm for W and top tagging and Z tagging at DLHC, at CMS, 30% efficiency as it has 10 to the minus 2 false positive rate. So it would be sitting here. And you see that basically our W tagger and our Z tagger do the same, except that we just use 50,000 events to train it. So with 50,000 jets, we are already as good as state of the art, before deep learning state of the art, with 16 features as input. Okay. And now you can take this and you can try to play with it. And the challenge is to try to get something better than this by tomorrow if you have time. And with this, I would like to get some questions and then maybe we close.
Jörg? Jörg Andres, can you? Okay, one question, waiting for connecting. You can speak. We cannot hear you if you're talking. Yeah, since your mic is not up while you're trying to fix it. Francesca, do you have a question?
Yes, I have a question about the decision of the number of nodes in previously. How do you decide how many layers you make and how many nodes it has, and if the result is going to change based on these parameters?
Certainly the result would change, and the way it changes is not obvious at all, in the sense that as much as people can come out with rules of thumb, like typical rule of thumb is that if you have, how many do we have? We have like 30,000 examples for training. What is it? We have 33,500 examples for training. I mean, it doesn't make sense to put something which is comparable to that. Typically, we like this number to be 10 times smaller. But then it's up to you to decide, okay, I want to put all of them in one layer or in 65 layers. Then there are papers, like there is a big deal of application. Sorry, let me switch on the light. So there is a big deal of literature that between statistical mechanic experts or physicists and applied mathematicians that tried somehow to describe the thermodynamic of this learning process. And based on that, they come out with recipes on what to do. So for instance, there are papers that, for instance, you can check it by Max Tegmark that describe the complexity of the network, and they show that the complexity basically grows linearly with how wide your layer are, but it goes exponentially with how deep your network is. So if I give you 600 neurons, it's better to have a deep network than a shallow network, even if there is a theorem that says that an infinitely shallow neural network can learn any function that is continuous, and I don't remember what else. So the fact that there is a function so basically the fact that there is a neural network that can approximate every smooth function under some smooth conditions doesn't mean that that is the network you want to use, because the fact that the function is out there somewhere doesn't mean you will find it. And so you want to instead play with more aggressive, deep architectures, trying to keep maybe the number of parameters under control. And it's completely empirical science at this stage. And then, as I was saying before, for instance, in the paper that I was referring before to, you will have the link in the slides, in the last page. What we did there was we did a Bayesian optimization. So we specified a search grid of parameters, which was how many layers we want, how many neurons per layer, a little bit of this, which optimizer, the learning rate, and so on. And then we wrote, rather than writing this piece of code that you see here, we wrote a function that was generating that piece of code as a function of these inputs. And then we ran a training over the trainings. And we were basically finding the training configuration that was giving us the absolute better result. And of course, computationally wise, this just explodes. And so people discuss a lot about doing training in parallel and parallelizing the model, parallelizing the data sets, and so on, because it becomes computationally heavy. So the short answer is that nobody knows. And then, of course, you have the concept of where the state of the art is, because I mean, as I show you with this very stupid example, we're already state of the art for what concerns the green, which is the W, and we're better than state of the art for the Z. And state of the art of when we wrote this, which was 3 years ago. Now people are doing this, and so this is the new state of the art. So this is a little bit, it's the balance between the good and the better.
Okay, thank you.
So, hello.
Yeah.
Does it work now?
Yeah.
Yeah.
So can you hear me now?
Yes.
Good. Okay, very good. Okay, sorry. So I have two small questions. First of all, here in this chat example, we are doing unsupervised learning. Is that correct?
Oh, supervised.
Okay.
Because you see it here. Wait a second, I'll show you. That we specify a target. So you have an X, you have a Y. And basically, the output of X has to match Y. And we do this with the cross entropy, which is the function that I showed you in the lecture, that is basically corresponds to a 5-dimensional Bernoulli problem.
Okay, so this means in our test data, we already have basically the tags, so which chat it is.
Because
okay, so where do we... Sorry?
Because this is simulation.
Okay, it's a simulation. Okay, so this was the other question. So how do we know what kind of chat it is? So this is
typically what people do is that rely on the simulation to build the training data set, and then of course you have to pay some systematic uncertainty for data Monte Carlo differences. There is you can Google. There is an explicit example for jet tagging, I think also. There is something which is called weakly supervision, which is a technique by which you run something in between a supervised and unsupervised learning. It's unsupervised in the sense that you use unlabeled data, but you bin your data. So you say, this is subsample 1, this is subsample 2, this is subsample 3, this is subsample 4, in such a way that the relative composition of the n classes you want to separate is different across the categories. And by this construction, even if you don't know jet by jet which jet it is, you can still learn how to separate them, because it's basically like running a bin fit. So if I give you a class which is 30% bolts and 70% squares, and in the other jet is 50-50, the network will figure it out with this kind of classification. So there are ways to train directly on data. On the other hand, high energy physics at least is in a relatively good position because our Monte Carlo is pretty good. And so even in the Monte Carlo simulation is not 100% accurate, it's a very, very good baseline to start with. And then you have a posteriori, you have ways to go back and check that the performance that you obtain are the same as was the Monte Carlo promised, which is true regardless of the fact that you're using machine learning or not.
Mm-hmm. Yes, okay, understand. Thanks.
Yes. Yeah. Any other question for Maurizio? Okay, Maurizio, thanks a lot for your first.
Yeah, the last thing is that I wanted to put so I'm putting it on the chat, the link to the GitHub.
Yeah,
and there is also the PDF of this lecture.